the Dr. Muhammad Ijaz from the Manchester Metropolitan University. Okay, please.
Thank you so much. Hello, good afternoon, everyone. And good morning, and good afternoon to whoever is watching online. I think we are also online. So, first of all, I think I will start with word of appreciations, particularly Dr. Ismail. Thank you very much for your invitation and also a wonderful event we are into. And so far, I think we are doing very well. And then a lot of young audience I can see, and of course our very senior audience who are giving us feedback and so on. So a little bit introduction on me. I'm Dr. Muhammad Ijaz. I'm a reader at Manchester Metropolitan University, and I'm also head of laser and optics communication lab within the university. I just put a picture of our university just on the back. This is our new build for Faculty of Science and Engineering. And the purpose of that is you have to come and visit us and see our wonderful facilities, So that's like a piece of cake for us, so we can kind of use that facility for collaboration and so on. So I will be speaking on visible light positioning. I know we've been listening that quite a lot of that from the center, from Ottoman, and Fari also discussed about challenges and so on yesterday. So I'm going to push a little bit more towards 3D visible light positioning. How can we use for unmanned aerial vehicles like drones and so on, particularly in the scenarios where we have Industry 4.0 applications and also smart warehouses and so on. I will also discuss about some of the challenges and advances in that. A little bit more introduction of my university. If you've not been in the UK, we are in the northwest of England, and you can see a little bit aerial view from the aerial. The Manchester is quite congested city, like similar like Santiago. I think it looks like twin cities, yeah. So we are located in the central location, and we are quite a big university. And within the central location, it's really convenient that when you visit, you will see all the city and so on. So we are somewhere in the top right side, Faculty of Science and Engineering, and we hopefully moving into the new build, as I showed you before, next year. Right, so coming to the point, to the business, yeah. What we're really gonna cover today, a little bit research highlights in visible light communications. I will just showcase you some of my research projects which I've done, and I will then introduce my own lab, my facility within the university where we can collaborate and further excel in our research. And then I will come to the visible light positioning, and we can discuss on that, some challenges we can discuss on that, yeah. So yeah, this is my lab at Manchester Metropolitan University. We have dedicated test beds. Just to give you some idea, I started on free space optics about 15 years back with Professor Fari as an MSc student, and I did my PhD under Professor Fari. I'm really, really proud of being his student. And the chamber, maybe you saw here with Stanislav, basically I'm really proud to tell that I started that work. No one in the world has that chamber, and Fari asked me to do some control study on FSO and channel modeling and channel measurements and so on. And because the weather in the UK was very unpredicted, sun is not there, fog is always, and then we need to measure turbulence that we need to do quickly, the measurements and so on. So we really started that work, and I am glad that many other universities have that test chamber, so I'm really proud on that. We published a lot of work with our European colleagues and so on. But I'm also looking into visible light positioning, Wi-Fi visible light positioning. I did some work with Professor Hutterhall in visible light communication, Wi-Fi links, which I'm going to show you some of the work. And the young generation, we're really happy to share our resources to help you in your research. and you can work with us and so on in collaborations. So I'm looking really all of these areas, but in context to 6G, sorry if you mentioned that bloody 6G, we learned yesterday, but we need to go with the pace, yeah. So we cannot just stay in 4G and wait, okay, let's do everything in 4G. We need to go with the pace so we can go for funding and so on. So I'm looking really in context of 6G or maybe beyond 6G, we should say that. Visible light positioning is one of the candidates within that. And I'm looking on visible light positioning, so I'm going to show you some of my PhD students' work. My PhD students' work. Yeah, not my. He did a PhD. He was from Saudi Arabia, wonderful student user. So I'm going to show some of the project. Free space optics. Jamie discussed a lot on free space optics yesterday, but I did some work in free space optics and I have test beds and so on. We are looking into from optical towards terahertz as well. I think this is one of the areas which we think that it will sit in 6G, yeah? So we need to really consider that as well. So I'm looking at terahertz. Of course, I've done work in signal processing, modulation schemes and so on, mostly MATLAB, yeah? I use, yes. With the communication and connectivity, I think the latest other application like IoT, machine learning, and also AI, we are really, really important. Finally focused that yesterday on that without connectivity, we can't work, in those areas. So I'm looking within that areas, IoT, AI, and machine learning. I'm going to show you some of my projects with industry in that, yeah. So in terms of, because we are doing research, so the collaboration is very important, yeah. So you can see when you do high quality research, collaborations comes automatically and we work together and so on. You can see that we are collaborating from Manchester Metropolitan University with University of Santiago, University of Chile. Maybe few of you have published a paper jointly with us. So you can see that on the right side, Dr. Caesar, Dr. Ismail visited us, and Raul also visited our lab and so on. So we did work. So we are open for collaboration, yeah? Right, few hardware which we have in our laboratory. Basically, this hardware is established by undergraduate, postgraduate, and PhD students. We have Li-Fi low-cost links up to 10 to 20 megahertz bandwidth. We are looking, high bandwidth devices as well, which I work in during my PhD. But I think, generally speaking, off-the-shelf front-end devices, like optical devices, are low bandwidth devices. So we need to really we are limited with that, and we need to use those. So some of the hardware which is in my lab, which potentially can be used to test our theory and so on. Yeah, we use usually laser sources for FSO and so on. So we have everything in the lab. We are also, of course, working towards to commercialize system. So for that we really need to see how can we make real time links where we can transmit maybe just sound signal with low cost, low bandwidth devices, and going towards video signals. So one of my UG student final year project, he tried to make under $10 a Li-Fi transceiver, which is capable to transmit audio signals from phone and to speaker, yeah. So then he made a channel and everything, and he is now in industry, working in industry. That's his project. So we are really focusing on the application side of the technology. We know that we are trying to achieve multi-gigabit per second using VLC, but if it's not usable at system level, what we're going to do with that? When you implement at system level, you may get 10 megahertz bandwidth or 10 megabit per second, but you're demonstrating I can achieve 100 gigabit per second. I don't know really how we will use that at system level. That's the challenge. Really, we need to focus on application at system level for this technology, which I think we are behind for now. And I know Ottoman is working with space agency. That's the way we can really try to commercialize our systems. Right. Within my laboratory, I work with industry. This is more UK-based industry where we have funding available from within several projects funded by Innovate UK. But this is a collaboration with industry. And what we really try to do, rather than we do a lot of research, can we commercialize it that well? So this is really a good example that companies are involved. They're not looking into research, they're looking into product development and commercialization and making money and so on, and impact. So we work with I work with 3 companies within the UK from last 3-4 years, and I got about £1 million funding from the UK funding bodies. Yeah. So this demonstrates that we are able to get funding. We can do that, So between Chile and also UK and France, and UK, we can apply for those funding as well with industry partners. I think this is boring for you people. I think we've discussed this a lot, yeah. But we all know that in visible light communications, the idea is to use visible spectrum for data transmission. Few people talked about we have illumination, can we use that? So this is all visible light communications. I believe the difference between visible light communications / Wi-Fi, people say Wi-Fi is more network system where we have all layers, but visible light communications maybe I'm wrong, yeah, but is more physical layer technology, yeah. So that's the difference between visible light communication and Wi-Fi, because Wi-Fi is similar as Wi-Fi. So when we look on the system level, then we consider all 7 layers, So that's the difference. And I know that people know about optical spectrum, people say it's unlimited and so on. So, but few companies are really working into commercialize this technology. For example, a lot of companies, which I think I'm going to cover in the next part of the talk. Well, I think Fari discussed about 5G, and also, he said we're going towards 6G, but 5G, we still not really explored our potential of 5G and so on. What 5G demand is that we needed higher data rates. But I discussed with Fari yesterday during talk, and he said maybe for IoT we don't need high bandwidth. We just need a low data rate, which is really true. Yeah, we really for IoT sensors we don't need high bandwidth. Maybe just medium bandwidth and so on. Yeah, so that's fine. We can work with any bandwidth or data rates, yeah, in 5G. But the intention is for mission critical systems like AI and the driverless cars and so on. We need maybe high data rate and also very low latency, and also massive connectivity, another pillar of 5G. And we believe that visible light communication, or in generally optical wireless communication, including free space, everything, can provide that all 3 bullet points or pillars, yeah, to the 5G, yeah. And we've said many times that this technology is a kind of complementary technology. It's going to help the existing radio frequency system, yeah, and in a way that working together we can support the full system level implementation for 5G and so on, And also Barry mentioned about we look integrated big systems and so on. That aspect is also, we can use that as a 5G technology, the visible light communications. Well, there was a little discussions on would OFDM is the modulation scheme for the visible light or Wi-Fi low bandwidth devices. And I think yes, because we have the off-the-shelf devices like bulbs, yeah, the light fixture, these ones, yeah. And these light fixtures have limited bandwidths, it's fixed bandwidths, and usually it's low bandwidths, up to maybe 5 to 10 megahertz, and maybe some high power LED-based bulb maybe have maybe 20 megahertz, but I'm not sure, but usually 10 megahertz, let's say. So we really have a finite slope when we try to modulate that. It's not like a clear rectangular pulse. So we have a finite pulses, yes. So this really is a problem for us. We have really limited bandwidth on the devices. But I know that how the system works, you know on that, so I'm not really going to spend time on that. But I think we have a limitation from the devices. For that, to use those limited bandwidths in terms of enhancing spectral efficiency, which I think Altman also discussed yesterday, we really need to go for higher order modulation schemes such as OFDM. And OFDM, our colleague just discussed on OFDM, so I'm not really going to go in details. But OFDM could be a modulation scheme. Let's say if your channel is now flat, and if it has fading, multipath fading and so on, then maybe using adaptive power and bit loading could help us to gain better spectral efficiency, which means that we have a deep fading, or maybe we have a sudden fading in the channel. We can ignore that, and we can pack maybe higher order modulation scheme where we have a higher signal to noise ratios or power of the channel, and if we have a lower signal to noise ratio, we can pack, maybe we can send lower order modulation schemes such as 4 QAM or 16, but where we have a high power of the channel, we can send more bits there. So in a way, we can really utilize our channel more efficiently if we have a FDM modulation scheme and such like those, so we can use that. Now, during my postdoc, Professor Helen asked me, can we implement a spatial modulation to enhance further spectral efficiency? Remember, in OFDM, we can only send a log of 2 bits per hertz, per hertz, but we can additionally add more bits depending on the number of transmitter size or the MIMO size. Basically, spatial modulation is a MIMO modulation scheme where you need to have a MIMO system. So basically, if you enhance your NT, you can add more bits with the OFDM, and hence you can further increase your spectral efficiency. Remember that we have a limited, bandwidth from the devices and so on. So basically, you can encode data in the position of LEDs, and based on the incoming bits, we can then translate those data into different QAM levels, into using QAM modulation scheme with OFDM. So we can enhance certainly more spectral efficiency using this mathematical equation and implementing the OFDM with spectral modulation. And I did some experiments. The idea was, can we use massive MIMO using VLC? So at the time, we've been working with one of the universities in UK, Strathclyde University. They manufactured these micro LEDs. It's a cluster with many LEDs. So the idea was, can we use these micro LEDs for application like in this LCD? So LCD has, let's say, many micro LEDs. Can we transmit data through the LCDs in some applications, maybe IoT and so on, And we tried that one, and idea was, can we use higher data rate using these ones, because these were low output power LEDs, but has a quite big bandwidth up to 250 megahertz. So we did some experiments by looking at data rate and also the coverage area, let's say, the semi-angle. So you could see that when we have a very narrow beams, like laser light beams, which is really not practical for system level, but we've been able to achieve very high data rate, up to gigabit per second. Essentially, this can be, gigabit per second can be 5G data rates, because we're looking for gigabit per second and so on. We can achieve that. Now the question is, how can we keep it constant rather than it goes downward like that? I think we can do that if we have a more powerful LEDs. Then maybe we can keep that data more flat. But as I open the angle to get more coverage, the data rate drops almost exponentially. So up to 12 degree semi-angle of the LED, we have lost a lot of power at the receiver. And as a result of that, we are dropping our data rate. Remember, your data rate is a function of your signal to available signal to noise ratio and so on. So we did some experiment, but the challenge is, because of the low output of the LEDs, when we open the semi-angle with the lenses, then our receives power drops. As a result of that, we are dropping our data rate and so on. Yeah. But I think some more work needed in that to make that line constant really. So maybe this is a next research project. So I don't know. In terms of commercialization, for the I think I took that slide from Fari's slide. I don't know if Fari has a similar slide. So sorry about copy. It's not copy really, but
No.
yeah. I don't think so. But I saw your slide and I thought I should show that. Yeah. So I'm trying to get permission for Fari. But I think this slide really shows that we are really going towards commercialization. I know there are challenges, still challenges. And the challenges could be mobility, maybe blockage. Some of the presented on the different, the relay system as well. If there's blockage, you can use the relay system. Stan presented that, I think, one. So basically, we are in the phase of commercializing this technology. Simplified is the big company involved, and also Pure Life, Five-From Edinburgh, and other companies are also involved. So we are going towards commercialization for that. Okay, so I think one of my students, I give him a project. Can we work on something like more green and sustainable solution for transceiver design? I think some of the works have been done by Carlos with Ottoman on solar cell, but I think the idea is same. We have about 15 billion IoT devices connected. And remember, those 15 billion require to power those, so we maybe need power infrastructure. So this means we are really consuming a lot of power. So we are looking to power these devices. Can we use solar cell as a receiver? Somewhere here, solar cell, yeah. So we took a solar cell from Amazon. Yeah, it's a commercial off the shelf. Yeah, and we go for that because it's cheaper there. So we took 4 centimeter by 4 or 5 centimeter by 5 centimeter solar cell. And idea was to use them in a MIMO configuration. It could be trending MIMO, where we have same in a series or parallel, or could be separately connected. The solar cell has not a very great bandwidth. That's the challenge. So this means that we can only transmit low data rates on that. So we try that if we can configure that solar cell in combinations like 2x2, 4x4, 8x8, and try to see if we can, how can we use that really, investigation. And we use LEDs, white LED, golden dragon. These are very high power LEDs. Maybe you can also use a good bandwidth of up to 10 megahertz. So try these LEDs if you really need good LEDs. The golden dragon is also available commercially, yeah. So we use these two devices and then we power it with the AC signal and DC signal. And then we characterize DC system, and then we also look on AC characterization as well, like sending data and so on. We use oscilloscope to capture signal, and also we use voltmeters and ammeter to measure currents, and we then use charger and battery to charge, and then again charge the system. This project is still in the way. We're not finished yet, but some preliminary findings from the student, which we aim to publish in CSNDSP conference. So we tested with 2x2 in series and parallel connection for the receiver. And we believe the experimental results shows that if we connect solar cells, doesn't matter the number, but we consider 4x4. We can get more bandwidth with the about 71 kilohertz with the solar cell in 4x4 configuration with these triangles, which is basically 4x4 in series. So the 4x4 in series, if we connect them in a series, not in parallel, we get higher bandwidth. This curve is on the top, yeah. And this is because we get more signal to noise ratio. Yeah. And similarly, we looked on energy harvesting, and you can see that 4x4 in series Comparing to parallel configuration, we are getting more energy harvested. Remember, in radio frequency, we get maybe less than maybe less than that. But in optical systems, we can harvest more energy comparing to radio frequencies. Yeah, people are doing research at radio frequency and so on. Yeah, so this means we can essentially use this technology to power our transceivers and so on. Yeah, because it gives us more energy harvested, 80 milliwatt. And you can then step up that energy and store it, and so on. And we did also data communication analysis. So we have a 71 kilohertz bandwidth. I think we've been able to transmit up to 100 kilobit per second. But this diagram is for 50 kilobit per second. So we tested the bandwidth, the DC characters, and also the communication. So we are able to transmit data on that. Now, next, I think what we're really trying is to optimize that link. This experimental test bed, and I'm really open for collaboration for that. Yeah. Okay, now I think to the main topic, which is my topic of the talk. So I'm going to look on visible light positioning. And this work is from my PhD, and I really want to acknowledge him, Yusuf from Saudi Arabia. He did a very good work within this project and published a number of papers, including journal papers. So visible light positioning, we know the applications could be, the tracking, the positioning, but mainly what we really focused on for industrial applications. In 2019, we started this project. At that time, there was visible light positioning, but generally in 2D, not in 3D. So this means we can only track movements on the XY plane, yeah, on Cartesian plane. But what about if we want to go in space, yeah, in indoor applications? So the visible light positioning has applications in transport and industry, and maybe in health for indoor localization and positioning. So basically, we use receive signal strength for the trilateration, and hence we are really doing the localization and so on. So you can see some of the examples for the indoor, but we are really doing this work in context to Industry 4.0, yeah? So why VLP? We believe that it can give a better connectivity when comparing to the radio frequencies, because let's say in tunnels, we've been discussing that VLC, is technology in tunnels and mines and so on. So we think that RF technology, when we go from towards the high bands, millimeter wave, so maybe we have challenges for indoor. So we can replace that with VLP for positioning and localization, and also for certain mission critical system, maybe radio frequency is not what we wanted. It works for us, but maybe we need more accurate positioning, yeah? So when we need more precise location, that we will say, okay, VLP is one of the candidates. And also low latency and high bandwidth because of this, it offers, yeah. And also because of the light luminars are very close to the receiver, this means that we have high signal to noise ratio because of high power luminars like these ones. So potentially we can use those property as well for that. And I believe it's, as far as that visible light is for the tunnels and so on. So I believe that this is ideal for smart factories and smart warehouses and Industry 4.0 applications as well. Yeah. So, such as one of the drone here is it's like a smart warehouse. Like UK has a very large postage system, big warehouses where we need to really restock. And maybe this is a quicker way to do that, but we can use essentially lightning infrastructure to localize or position that drone, and so on, or guide that drone, in other words. As I said before, we believe that VLP in 3D has applications in Industry 4.0 applications. This is because this gives us really very good accuracy, precise positioning, because of its properties like higher signal to noise ratio and so on. For example, if you want to, in industry where robots are robots' arms are working, maybe human are not allowed there because of the the health and safety. So what we can do, we can guide these drones with visible light positioning so that it can precisely pinpoint drop or maybe place the components on the arms and so on. Yeah, so we can potentially use that, and also for stocking and so on, in the factories. It can also greatly cut costs, we believe, yeah, because we have infrastructure, so we can use that existing infrastructure, yeah. Right, so we started implementing this system, and we considered many options really, and then we started with the simplest one. So simple one is you take a large room, yeah, which rather than you go for 5 by 5, we consider a very large room, 15 meter, and 5 meter height. And we consider this system model where we have a kind of track, a real track, and we want to localize drone around that using visible light positioning. And this is 3D model with LEDs on the top. We consider 15 LEDs, yeah. And also, this is a kind of the same track from the 2D point of view, so this is the same one but in 2D. But you can see some angles, and so on, which can be challenged for VLP, and we consider those as well. Before we start our algorithm, we also consider that we need to really consider light luminaires, like commercial ones, which can output up to 80 watt power each individual, and as a result, we need to eliminate all that big warehouse, yeah. And so we consider 15 of them, and you can see that it is really meeting the most of the the EU standard of 270 lux, yeah. So we did some simulation in Dialux. This is open source software usually used by designers, so we can use that really to look into, okay, if we consider this semi-angle of the LED 45 degrees, how many luminaires you need. So you can calculate your light fixtures from that software and so on. So we really tested that before we implemented our system, and then we consider same luminaires in our simulations with the parameters here. So you can see we consider 80 watt luminaires with 45 degree semi-angle, and so that we have a similar coverage in the industrial environment, and also you can see some other properties. But what we did, we implemented them. So the luminaire we consider from Osram, second generation, is a compact high bay light fixtures. It's available in the market. You can use that. It has semi-angle and also the power, everything up to 150 watts. Yeah. So then we consider this is a simple channel model for VLC. So we use that DC gain, but trilateration we need at least 3 light fixtures to do that. To measure the distances to perform trilateration algorithm. So we use that again. These are some of the standard mathematical equations, but I think the main point here, if we know most of these parameters, including your power received, we can calculate this distance. And this is exactly that distance, yeah, between that and that. So we're doing the other way, rather than we measure receive power, we're calculating a distance between transmitter and receiver. And that's exactly what we need really for trilateration methods, yeah. So once we have this distance, we can perform our trilateration algorithms. And we compare 2 trilateration algorithms, which is in this paper. You can read that. We use Cayley-Manget determinant. This is shortly it's called CMD for the positioning. And also we compare with the classical linear least square method, yeah, which is everywhere, radio frequency and so on. Yeah. So we consider that one with these 2 algorithms, which I'm going to show you in the next slide. And we also consider tilt. So you could, when you in a spherical coordinates, you have azimuthal and also the tilt. So usually the drone tilts when it moves like that. It don't stay stable parallel. So this is your parallel system comparing to that. Yeah, usually we consider that when we do channel modeling. Yeah, this is your parallel. But the challenge in drone is it's like when tilted. Yeah, so then you may have a different signal to noise ratio when you compare like that. So we consider that with that simple mathematical function, and we also tested with this with this tilt as well, our system. And once we theoretically did our our mathematical work, then we think we need to test that with experimental test bed as well. So we have a great partnership with the University of Ghent, with Professor David Plex, who's very good in radio frequency. And honestly, we met in the CS and ESP conference in Hungary, and we met in Suana, just in the swimming pool, and we started discussing, and we thought, okay, we can collaborate. He showed me his radio frequency research, and I said, okay, my PhD student is also working in VLP. He's doing positioning with radio frequency, so we share research and we benefited. And this is his laboratory with the high power similar LED Osrams. We have 4 LEDs on that and single receiver. And the way we implement it, we use Adafruit microcontroller. We send FDM, different signals, and then we capture that with the receiver. And then we calculated the receive power, really, DC receive power, to perform our algorithm. We did it in frequency domain, the analysis. We use this is from Torlab, one of the receivers, which I think the guy also used that, from Brazil, Okay, so simulations, everything works very perfectly, no challenge, as Maria always says. So what we have really, we compare CDM and Calle-Mandri determinant algorithm with linear least square. This is a standard one just for comparison. We see that similar kind of performance. The maximum matters 90% about under 5 centimeter, let's say 5 centimeter. The median is about less than 1 centimeter, which shows that it's perfect positioning. We also use cost function. We have, well, the challenge was how we will measure height, where our drone is, When we use Calle-Mandri, then we have plus and minus, which means the position can be there or there. Above or so. It's like positioning ambiguity is called. So you have 2 points. So we need to ignore one, and we ignore the one which is outside the top one, because this is beyond life. So we consider that point, and then we consider this is our transmitter and this is our receiver. Then we took maybe 1 million heights, and then we perform the cost function to minimize that height. Where our function minimizes, that would be the height. So this is how the cost function works. So basically, you make in small sections, and then you have a large set of height vector, and then you minimize that where the minimization will be. That would be your height. In this case, it's 2 meter. But you can see that with tilt, the minimization is really not optimum, because this should be 0. But with that could be some errors. Because with the tilt, your receive signals to noise ratio drops. As a result, this band would be more flat. So that could be a challenge, because of the tilt. But we looked at experimentally later on, and you can see that this tilt is 5 degrees. So it's not a very big tilt, but small tilt, and still you have some chances of error, which you will notice later. Now, so simulation, everything works, but when we implemented experimentally on our test bed, you could see that the positioning errors for both the algorithms is increased. This is simulation under 5 centimeter, but this is the 10 to 90%, the median errors, you can see that is about 15 centimeter. So 15 centimeter, maybe not ideal for the Industry 4.0 application. If you need to drop or place the part within 5 centimeter, so you are beyond your accuracy, so that could be a challenge really. So practically it looks like challenging, but theoretically it's working. That's the conclusion from here. And even when we consider, we're not really considering azimuthal, but we're considering tilt, that tilt. We're not considering that one, we consider that one, And you can see that when the drone moves, the angle also changes. Azimuthal also the tilt, And when you consider that concept into your simulation, you can see that your eye errors further goes up to 90 centimeter, up to 1 meter. And we make business case that VLP is kind of better and precise, give you precise positioning when comparing to radio frequency. But I believe this is still better than radio frequency. I believe so, but I don't have data to really compare. So this is my kind of idea. Maybe you can comment on that later. But you could see that with the tilt of 1 degree to 5 degree, we have we increases our CFD, the median and the maximum, for all the algorithms. So that you can see also 1 meter up to 1 meter, the positioning errors goes up until Now, we further enhance that. We optimize that with machine learning, which Rahul is going to present his paper on that. Yeah. So we try to reduce these positioning errors with machine learning algorithms. Yeah. Rahul will throw more light on that later on. Okay. So one challenge we looked on the tilt and so on. Another challenge could be, because we are in an industrial environment, we make our case that we are going to implement our system in industry. That industry could be where we have manufacturing, like a lot of fumes and heat and so on, or maybe where we have the trash and everything we reprocess and so on. So there could be some kind of dust and so on. So ideally, this should attenuate our light because of the particles and so on. So we consider that in our simulations, and I'm going to show you results later. But we have another challenge. Let's say we are when you have a high ceiling, yeah, in an industry environment, maybe your light's like hanging, yeah, and as a result, if your drone needs to go up, so you are in a dead zone. You don't have the signal to noise ratio because of the beam of the channel, So what we really consider here, we consider two light fixture, 3 and 4. Our EV is up to 3 in iteration, yeah, tri-iteration. But we consider up to 4, and you can clearly see that when we have a less than 4, you see that we have more, the coverage here. So the black one is more dead zone. So as the number of light fixtures are dropping, we would have more trouble. We would have more dead zones. You can see that way here. And therefore, I think we need to consider at least 4 light fixtures instead of 3. But 3 we needed. But I think linear least square, we need more. We can use more light fixture. But in our analysis, we consider just the 3, which are the strongest one, the closest one. When drone move, we just consider the closest one. So that's the challenge. You can see the results from that. You can see that the achievable heights with basically this is all trigonometry, the channel and so on. You can see that as we increasing our semi-angle field of view of the light fixture, depending on the number of the TX, this way the depth zone, the maximum height, So as we increasing that the field of view, we are getting more height, yeah. So this means we need to get more opening of the transmitters, rather than it's more very focused. All right, so this challenge is there, but I think it's not very crucial. We can tackle that. It's all, the system level implementation, so we can tackle that. In terms of attenuations, when there is that environment where we have different attenuations, what we really have is the attenuation in the receive power. You can see here in this result that when we consider visibility, we use visibility models to basically consider attenuation. When we have a visibility of 300 meter, we have more attenuation here. You see than the 1 kilometer visibility. So the conclusion from this slide is when we have the polluted environments, then you will lose your signal to noise ratio because you're losing your receive power here. You can see here the ideal without any attenuation and with attenuation of different strengths and so on. when you have received signal to power ratio, receives power drops, then your receive signal to noise ratio also drops, so you can see in this slide. Right, because of that attenuation, you can see that then we have some challenges in the accuracy of the positioning, and you can see that the real path is this line, the red line, yeah. So we want, and this blue is with AWGN. So this is fine. This is quite a good match between the two, yeah. But as we have more, polluted environments, then we have more attenuation. With 1 kilometer, we have low attenuation, which is green one, which is closest to the red, and the blue one, which is fine. But as we have more attenuation, we are going further away from the real path, which we intend to do. And I think this is really a kind of business case for your further research, because you are looking into Nicholas, yeah, and your group here. So yeah, so this is the one you could see that with attenuation, the positioning errors are increasing, yeah, and you can see from this slide, yeah. So this shows that the positioning errors are increasing when we dropping our visibility. As a result, your signal to noise ratio will drop, and as a result of that, your positioning error are increasing, let's say from 10 centimeter to 40 centimeter, yeah. And similarly, this is when you have kind of dry particles, but when you have a kind of humid and also like wet particles, you can see again that similar trend like that one. So with the less number of pollutants, you have less attenuation, and as a result, you have a low errors, and this is increasing with the increase of the attenuation and so on. Yeah. So yeah, so this is a kind of another challenge, attenuation. Yeah. So we have done then some. Another challenge is the intersymbol interference. We still have that challenge because we have reflections in the. Let's say if you have an environment where you have a lot of racks, different, the paint, the color of paint, and so on, then you have reflections from that, and that could be a challenge. I haven't done really much work on that, but this could be one area that can be looked into generally across the different, visible light positioning. It could be, I don't know if this is a challenge in camera communication, but this can be in photodiode case. Right. So after these challenges, what we really did in this paper in SACVLC, which Rahul is going to present later, we think that let's try with machine learning algorithm and see can we able to optimize our system. So we have this algorithm which we really adopted from radio frequency or from simple maths, and we calculated positioning error. We have a large data sets of error up to millions in length. The sample rates of errors were multi-billions. Yeah. So we have a large data set, and then we train that data using ANN model, and you can see that this is our target. And when we increase our the iteration at 1,000 epochs, we are able to meet we are able to train our model, up to 1,000 epochs, yeah, and you can see from the histogram as well. So we use that ANN machine learning model, and we then show that this is the case when you have attenuation part. You see that this is quite scattered. And away from the red part, yeah. So we have a very complex path within a big room, and I think the number of data sets is very large here. And then we train that data, and after training and the algorithm, we found that we are able to minimize our errors, which can be clearly seen in that graph, so that the red and the blue, after the machine learning algorithm, we are able to make compensate the errors from 21.9 centimeter to 5.9, about 6, which is about 3 or 4 times better than the without machine learning. Now this has some computation power involved and so on, which Rahul is going to discuss in his talk. I think that's it. So I just really covered on some of the aspects on VLC and also visible light positioning. We have strong experimental and theoretical research in optical wireless in different areas. We really aiming health, transport, smart infrastructure, and also industry research. Professor Jamie is there. We have also done work in free space optics, and we are really looking forward for that as well. We have state-of-the-art facility for collaborative research. I collaborate with Professor Fari as well, and really opportunity to work together, and also we will benefit, mutual benefits and so on. Thank you very much.
Thank you, Muhammad. Because we need to move forward to the session 6, I will offer only a couple of questions. I hope that all the people want to do questions after this excellent presentation, but we need to keep our timing. Someone has question? 2 questions, please.
Yeah, maybe I should go.
Yeah, go ahead.
Ijaz, thank you very much for your presentation. It's so lovely to see your research is established, you're collaborating, you're moving into new postures, you're exploring unknown topics, and it's great for me as someone who's associated with you, and that is a very nice feedback, and I'm very proud of you. My question is that when you're looking at the flying objects and you talk in detail about the height, I think one of the important things maybe one needs to consider is that because you're using the illumination LED, these LEDs, their first purpose is illumination. Therefore, the level of illumination hits the eye safety standards. And therefore, that comes first. In a manufacturing environment, illumination also level is set by the health and safety standards. So therefore, if you open up the field of view in order to gain extra high, that means that you've got to increase the illumination level, which means it's going to hit the threshold of ion safety. So did you consider this in your talk, that you have an upper ceiling that you cannot go beyond that because you will make people blind? Yes?
Yeah.
So therefore, I don't know whether you have possibly have considered that or so, how maybe that could be incorporated into the future.
Sure.
Look at the boundaries and limitations and so on.
Yeah. I think that's very valid question. I think we try to tackle that with this one. Yeah. This one. No, that's just the kind of analysis which you just elaborated. That's fine. That when you open up angles, then you get more coverage. But other way, when you close, maybe you have more intense light and so on. I think maybe this answers your question. I don't know. We consider that illumination lux of 270, 80, which is standard European standard. So we reported that in our publication as well. We to keep that health and safety and high risk, we just use that one really standard. I don't know, maybe this is what you think, or maybe.
Yeah, I mean, if you look at this room, look at the upper here, the darker than here. For me to make that is like I've got to pump in more light.
Yeah.
And that's when we hit the eye safety.
Yeah.
So therefore, in your algorithm, you have got to incorporate your threshold level.
Yeah.
But you cannot go beyond that because this level.
Sure. Makes sense.
That was my
Yeah, exactly. We looked on that. Yeah, that's your answer to the question.
So that is within the eye safety limit.
Yeah, 282.
And therefore,
at a working place on here. So this is the standard, the EU, that number. So we try to maintain. Of course, we get some 400 here. Yeah, we get 40, but we are going to box standard. You're right. Yeah.
Yes.
No. But for a fixed system, this will come you somewhere you get more. That's a valid question, and we try to tackle that here. Maybe not 100%, but we try. Yes.
So why is it the ISR of concern to you in position?
Well, we did some experiments, and I purposefully didn't put those results. It's published, and it really deviates the positioning from the standard, so it adds more errors. And I can show you maybe later after the program of that.
Thank you.
Yeah.
Okay, I have two quick questions. Thank you, Ijaz, for your presentation. Very nice. Thank you so much. I just have two quick questions. Firstly, from the point of view of having a PV cells as a receiver. So I've seen that the bandwidth that you're showing around 40 kilohertz, something like this in kilohertz, right?
Yeah.
And you were saying that is it like a MIMO system where you do a carrier aggregation, meaning that you do 4 receivers and you aggregate the bandwidth for them together?
Yes, kind of, because we just send, it's a series in the series. The series give us more, so this means that the same signal goes through our board.
Okay.
Yeah. So
But does that meaning that I'm adding the bandwidth? Yeah, here.
Yeah, kind of, because you're adding the bandwidth, maybe your product is getting bigger area and so on. But I think you get more signal power. That really results in
So it's like the concept of MIMO system.
exactly. Yeah.
So, but the bandwidth of this, you can see the 70 kilohertz. Because to me, is that for me, this is very big number for a photo cells as a receiver.
Yeah.
That's why I'm asking.
The photo cells are very small,
Yes.
like these ones. So maybe that's why.
So you actually.
And it's
combine
a monocrystalline are maybe better than polycrystalline. So that's why. That's really major. We believe,
Very
this is-
interesting though, but yeah, this is my fundamental one.
Yeah.
And my second question was related to the drone drone positionings, because I actually not familiar with that drone concept. Assumably that we are outside and we have this, this now texture that you see this advertisement where you have a lot of drones out there. I'm wondering what kind of positioning system they are using for that. Have you looked by any chance?
Well, this could be GPS kind of technology, radio frequency.
Mainly GPS.
Yeah. But me and Sujan published on BLC, but it's 2D using lights, outdoor lights, the light fixture. So we published that in a DPI paper. So yeah, we tried with BLC as well, with street lights in a linear way. So we should have a 3 in a linear combination, the street lights. We tried that as well, and it worked to some extent. But again, the challenge is that we don't have light, as Fadi mentioned, we don't have lights all the time on and so on. So yeah, I don't know if I'm answering your
All
question.
right, no, thank you so much for that.
Thanks, Muhammad, for your presentation. Very nice presentation.
Thank you.
As we know, we are working on visual recognition system also.
Yes, I know.
And
I know.
you can see the previous presentation on this cover.
Yeah.
Because we have a lot of problem finally for business.
Yeah.
And for example, if you go outside on the border,
Yeah.
with the drones, maybe you cannot do recreation because you do not receive information from free
Sure.
sense.
Yeah.
So, as you know, and mentioned this with that different. So, I think it's very important in this topic to go to resilient positioning system.
Exactly. Yeah.
So,
I
it's
want
just
to-
a remark.
Sure.
About collaboration.
Yeah,
I think it's because we are working in community of positioning, not
Exactly.
only visible light, but
Yeah,
also
100%.
technology.
Yeah.
I think we have to move to this type of
I think
work in the community of
Yeah.
positioning, indoor positioning. We have to move for resilient positioning.
Sure, yeah, I think this is a really amazing topic and really new for me. And I hope I will learn from your group and then we can jointly collaborate with Chris and with your group. So I look forward to it. So, yeah. Thank you so much. Any more questions?
I have just a comment for the fire question. There's a couple of papers that treat the our location. When you can put the lights, they treat like an optimization problem. So
Yes.
number 2, there's the constraints about the limiting safety levels, but they don't consider the size of the drone. For
Yeah,
example,
Yeah.
because the drone makes some shadows
Yeah.
in the floor. So that could be
Exactly.
the next level to,
Yes.
but it's just the design process. They,
Sure.
and they treat the robustness of the design.
Sure,
So it's quite static and
I
it's
agree.
not dynamic.
I agree with you.
Yeah.
Brilliant. Thank you so much, everyone. for
Thank
listening.
you.